Hello, hello. Welcome. And I'm here with Tod Waight, Professor Tod Waight from the University of Copenhagen. And we're here in Copenhagen, and Tod agreed to have a little chat with me about his new research grant.
Yes.
And Tod has been successful in attracting a big splash of money for his new research ideas. And I'd like to grill him a little bit about that. Because, first of all, I think he's doing good stuff, and secondly, we all want to learn how to get big research grants, don't we?
Be persistent, I think.
Is that the answer?
Yeah, keep on trying. So.
Okay, tell us a little bit about how often did you have to try?
I think this application has been in 4 or 5 times at least.
Right.
And it's kind of been modified every time, sort of starting out as a relatively small project, which is now incorporated as part of something which is much bigger. And the interesting thing is we get reviews on projects when they go out and get sent in and stuff like that. And one of the reviews on the early stages of the project was a bit, this is a bit boring. There's nothing particularly sexy in this. And then I built it up and expanded it into a whole bunch of different things. And then with this little project still put in there along the way, but kind of getting toned down a bit along the way. And then this one, which I got, which was approved, they say, oh, and that aspect of it, that's really exciting, and that's something you could make even bigger. It's very much dependent on who gets to review things, but yeah.
Could it also be the flavor of the times changing? Or
yeah, it could
like
be.
That?
Yeah.
Yeah, I remember that I once had a research grant where they said, oh yeah, submit it again and enlarge it, and next time I got a comment like, oh, this is not so exciting.
Yeah.
And you kind of go, wow. But I assume it was different people looking at it.
Yeah,
indeed.
Yeah, they are different people who've done it.
Right. Well, in any case, you got a big, sizable chunk of financial support now. What are you going to do with it? What's the plan?
Well, the idea is to focus on the specific mineral, a mineral called zircon, which is it's not a particularly common mineral in terms of it's present in most rocks that you find in the continental crust, but in relatively low proportions. So it's a trace mineral. But zircon we like zircon a lot because it contains a bunch of elements that we can use as geochemical fingerprints for. Primarily for the age of when that zircon grew, so that tells us about the magma that zircon grew from, but also the composition of that magma and what was melted to generate that magma. So by looking at a few key trace element and isotopic compositions in zircons, we can get an idea of when a magma crystallized, but also the sources for that magma.
Right.
And so the idea is to look at the whole concept of the continental crust. I think if we live on Earth, as a non-geologist, you don't really think about that we have a granitic continental crust. But as soon as you start looking a little bit further abroad, then you find that having granites on Earth is something which is quite unique. You don't find granites on Mars, you don't find granites on Venus, you don't find granites on Mercury, and you don't find them on the Moon. So what's special about the Earth and why have we got them? And so that's the bigger question behind it, is kind of looking at when did the continental crust grow and how did it grow, and then to why did it grow. So that's the idea, and the other nice thing about zircon is it's a tough little sucker.
Yes.
So it's a mineral so it crystallizes, for example, from a granitic magma way deep down in the crust, 15 kilometers down in the crust. That granite can crystallize to a solid rock, and then just with slow tectonic processes, that will slowly come up to the Earth's surface and get it eroded away and eventually turn into a sediment and be transported as a sand and be deposited somewhere. That zircon crystal will be in that sand. That sand can then get buried again by plate tectonic processes, get heated up and metamorphosed, and then the rocks that it's sitting in now can be remelted, but that zircon will just go into that melt and then come into a new granitic magma that can go through this whole cycle again. And if we say that the new granite that it's come up in is from the Cretaceous, it's 100 million years old, but the original granite that it formed in was 1,000 million years old, we can pull a zircon out of a 100 million year old granite and date it, and it's 1,000 million years old. So it's survived this entire crustal process.
And there's no resetting or so whatsoever? Or?
Generally not, no. No, it's very, very stable and can do these sorts of things. So that's the idea. to look at those, and then we let nature do the field work for us. So instead of going out and bashing off a whole bunch of rocks, we can go to a modern day river system or a modern day beach and collect a bucket of sand, and in that bucket of sand pull out the zircons, and those zircons give us what we hope is a representative picture of the entire landscape that is being eroded and sourced into that river and eventually ending up on the beach. So we can use one sample to get a picture of the geological evolution of a large area.
Right. Yeah, that makes a lot of sense. So it's the placer gold kind of trick where where you see it coming together and you don't have to actually go around and do the sampling yourself.
Yeah.
The erosion is doing it for you. Yeah. Where are you planning to do that?
2 locations. So there's sort of two parts of the project. The first part is to look at Scandinavia. So basically it's going to involve a road trip. Basically a bit of a jolly where I hop in the car in Copenhagen and then just drive up to Sweden, drive up to Uppsala and visit you.
That sounds good.
Yeah, and make a few stops along the way and collect some buckets of sand and probably end up in Finland somewhere.
Right.
So sort of get sort of 5 or 6 samples from various big river systems along the way, and use those to try and get an idea of how has Scandinavia been built up. And I think the really interesting thing with that project is we already know how Scandinavia has been built up, or at least we think we do. And so that's an option for us to sort of to test the method, to say, if we start looking at these sand samples, does that actually give us a representative picture of the geology as we know it? Or are there going to be some aspects in that in these bulk samples where there are geological events but we don't see them? And then we sort of say, okay, why is that happening? Are we losing something in this whole process?
That's a really interesting question, this question of preservation. Are all the events represented? This is why I asked earlier about resetting. Could there be some information lost along the way? Of course, we all hope that zircons are resistant to this, but also erosion may not necessarily deposit the detrital zircons from all the various events in a certain spot. So you must be aware that there may be some gaps. So this is very interesting.
Yeah. So that's one way of testing it. And then the other option, of course, is if you see some sort of a spike in your sediment samples that you don't see in the geology out there, and so then you need to explain that as well. Yes. How does that work? Yeah. So that's one part of it. And then the other thing is to do a very similar thing, but on a larger scale, logistically a bit more challenging, and that's doing it in Greenland.
Whoa. Oh, one of my favorite places. I've never been there, but I'd love to go. Tell me more about Greenland.
Well, I mean, Greenland I've been there twice. It's a fantastic place to do geology. But I remember the last time I was there, we were flying in a helicopter over the most amazing landscape. And you could see the Atlantic Ocean Baffin Bay was on one side, and you could see the continental ice sheet on the other side, and then there was just kilometers and kilometers and kilometers of basically full exposure rock. And I'm sitting there in a helicopter with a little geological hammer,
right?
And feeling incredibly small and thinking, how on earth am I going to be able to get, I think I had 2 weeks, any idea of what's going down there with this little hammer? And that's maybe where we can start using these natural processes to get an overview picture.
Is this a new hammer?
It's brand new, yes.
Great. Oh, wow. I'd love to have a new one too at some point. Very good. So you want to sample the detrital zircons there and sediment as well in order to get the catchment, larger area catchment sampled in one little sample. That will maximize your time and effort, I think.
And the other interesting thing with Greenland is that it's, I don't know what the proportion is, but it's 75% unknown because it's hidden under ice.
Yeah.
Okay. But that stuff is still getting ground up and transported and coming out from under the ice sheet and getting washed out. So the chances there, I think, are potentially higher to identify things that we can't actually see because they're not exposed on the surface.
Yes, there's probably a lot more room for you to kind of push the geological history a little bit and add to it.
Yeah.
So let me ask some more kind of summary question towards the end. what's the big kind of thing you hope to get out from it?
The really big question that I'm looking at here, and this is why Scandinavia and especially Greenland are, I think, key places to do this, is to see if this process about how we make continental crust has been the same over Earth's history.
Right.
Because we know that there have been some things which have changed in terms of plate tectonic processes and stuff like that. And so is that something that we can actually see preserved in the Zircon record? And Greenland especially is very good, because pretty much we say that the oldest rocks on Earth. There might be some people out there who say they're a little bit older than there are in Greenland, but pretty much the Greenland ones were found first, so they're still the oldest.
You have to say that here.
I have to say that, yeah. And you've got a geological history that goes from 3.8 billion years through to, well, at least to sort of 100 million years ago or so. And Scandinavia is not doing too bad either. You know, there's some pretty old rocks sitting up in Finland, and you've got this progressive build-up of rocks in the continental crust in Scandinavia. So there's a prolonged history of geological history there, and so we can start to build these things up and see looking at how continental crust has grown, but put a time dimension on it. See if these processes have changed, because the ultimate impetus for doing this is there's been a couple of studies done out there in very, very different places. There's one done in Australia doing this sort of thing, one done in Russia, and one done in the continental US from the Mississippi River.
Oh, I see.
3 very, very different places, and they've done these sorts of things, and they get almost exactly the same results in terms of when things happened. They see peaks I can't remember the exact numbers now, but there's a peak at 2.7 billion years, and there's a peak at 1.8 billion years, and there's a peak at 1 billion years, and you see those in Australia, the US, and Russia. Very, very different places. And so is this a global signature? Is there something special that happened on Earth at 2 billion years
these times
that made these things happen?
Can you distinguish tectonic processes from the chemical record in the Zircons? Are you confident that you can say this is, I don't know, extremely intense subduction, or is there, say, more plume activity or things like that?
There are. So there's 2 parts to the project. The first is to do sort of conventional dating, and then hafnium oxygen isotopes. That tells us what melted. So we can distinguish between making new crust, melting the mantle and moving that material from the mantle to the crust. We can distinguish that from taking the crust and then remelting it to make new crust.
That makes sense.
So we can distinguish between those. The other part of it, and this is where it gets a little bit more experimental, and that's kind of a fingers crossed, I hope this works, but there's also a couple of geochemical traces you can go in and use, and you look at different trace element ratios and stuff, and they can tell you a little bit about the temperature of magma formation, and there are some indicators of subduction that you can use.
Yes,
So-
I think titanium would be very useful for temperatures, and
Yeah.
obviously wet granites would probably be cooler as warm granites.
Yeah.
Warm granites likely are more associated with non-subduction processes, etc. Okay, I get it. Fantastic. Thank you very much, Tod. And well, congratulations.
Thank
and
you.
good luck for your research.
Yeah.
And thanks for taking the time to talk about this. I think
You're very
it's
welcome.
been really interesting. I enjoyed this, and I'm sure students, etc., will like that too.
Yeah.
So thanks a million, and we say goodbye, and
Yeah.
all the very best.
See you later.
See you soon.